Let's solve the 6 free response questions from the 2024 AP Calc BC exam. If you're looking for the AB questions, those are linked in the description. This video has chapters, so you can skip around the questions as you please. Let's begin with problem 1. The temperature of coffee in a cup at time t minutes is modeled by a decreasing differentiable function c, where c of t is measured in degrees Celsius. For t between 0 and 12, selected values of c of t are given in the table shown. Part A asks us to approximate c prime of 5 using the average rate of change of c over the interval between 3 and 7. We must also show the work that leads to our answer and include units of measure. So c prime of 5 is a derivative, which we think of as an instantaneous rate of change. We can approximate it with an average rate of change over this interval from 3 to 7. That's just the slope of a secant line. So we'll calculate the change in the temperature and divide by the change in time. So coming down here to write our work, we are approximating c prime of 5. We're using this interval from 3 to 7 because 5 is in the middle of that interval. So with the given information, this is the best we can do. So we'll calculate the average rate of change over this interval. So subtract the temperatures, 69 minus 85. That will be our numerator. 69 minus 85. That's the change in temperature. And then we just need to divide by the change in time, which is 7 minus 3. 69 minus 85 is negative 16, and 7 minus 3 is 4. So this is negative 4. The degrees, the temperature, is being measured in Celsius, and the time is in minutes. So this is negative 4 degrees Celsius per minute. That's approximately the rate at which the temperature of the coffee is changing at t equals 5. So that's part A. Let's move on to part B. Use a left Riemann sum with the 3 subintervals indicated by the data in the table to approximate the value of the integral of c of t from 0 to 12, and then interpret the meaning of that integral divided by 12 in the context of the problem. So let's begin with the left Riemann sum. Coming up to look at our table, we're supposed to use 3 subintervals, so we'll have to go from 0 to 3, from 3 to 7, and from 7 to 12. Now let's just sketch these rectangles that are making up the Riemann sum. This rectangle from 0 to 3 is going to have a height of 100, because this is a left Riemann sum, so we use the left endpoint to determine the height of the rectangle. The next rectangle has a height of 85, because that's the left endpoint. So maybe that looks something like this. That has a height of 85. And then the final rectangle has a height of 69 because that's the left endpoint at t equals 7. So maybe that looks something like this. Using this Riemann sum, adding up the areas of these 3 rectangles, we will have an approximation of the integral of c of t from 0 to 12, an approximation of the area under the curve. So coming down here to write part B, the integral from 0 to 12 of this temperature function, c of t dt, is approximately the sum of the areas of these rectangles. The first rectangle has a base length of 3 and a height of 100, so 3 times 100. The second rectangle has a base length of 4 and a height of 85, so its area is 4 times 85. The third and final rectangle has a base length of 5 and a height of 69, so its area is 5 times 69. This is part of the calculator section, so you can use your calculator to quickly find this equals 985. So that is our approximation using a left Riemann sum with 3 subintervals of this integral value. That's the approximation. But we're not done with part B, because part B also asks us to consider the integral we just approximated divided by 12. What's the meaning of that thing? Well, it's adding up the temperatures from 0 to 12, and then dividing by the length of the interval, dividing by 12. That's how you calculate average temperature. It only asks us to interpret this expression. It doesn't ask us to approximate it, though if we did want to approximate it, we could simply take 985 and divide by 12. But the interpretation is that it's the average temperature of the coffee in the cup over the interval from 0 to 12. Again, it's like adding up all the temperatures and then dividing by 12, the length of time. Moving on then to part C. For T between 12 and 20, the rate of change of the temperature of the coffee is modeled by C prime of T equals this expression, where C prime of T is measured in degrees Celsius per minute. Find the temperature of the coffee at time t equals 20 and show the setup for your calculations. So this will be pretty straightforward. We'll just take the last value we were given in our table. At t equals 12, we know the temperature is 55. And then we can use this derivative, this rate of change, to integrate and accumulate the temperature from t equals 12 up to the desired time at t equals 20. So down here for part C, what is the temperature of the coffee at time t equals 20? Well, it's going to be the time at t equals 12. So down here, what is the temperature of the coffee in the cup at time t equals 20? Well, it's going to be the temperature of the coffee at time t equals 12, which was given as 55, and then we will accumulate the rates of change from that time at t equals 12 up to the desired time at t equals 20. We're going to integrate C prime of t, which is given to us. So we'll use a graphing calculator and integrate this given derivative from t equals 12 to t equals 20. So pulling up the graphing calculator, I'll press the math button, and then I will press option 9 for the integration function. We are integrating from t equals 12 to t equals 20. And the thing we're integrating is this derivative, so we'll just be careful and type that derivative in. And rather than using the variable t, we will use the variable x, since that's most convenient on the calculator. So we're integrating this with respect to x, and we get negative 14.671. But of course, coming down to part C, we know that we also have to add 55 to this. That was the initial temperature, so to speak, at time t equals 12, which is where we started the integral. So adding 55, we get our answer of about 40.329, and that is in degrees Celsius. Finally, moving on to part D, for the model defined in part C, it can be shown that the second derivative equals this expression here. For t between 12 and 20, determine whether the temperature of the coffee is changing at a decreasing rate or at an increasing rate, and give a reason for our answer. We know that the rate of change of the temperature is described by the second derivative. So if this second derivative is positive in this interval, that means the derivative is increasing, and so the temperature would be changing at an increasing rate. If the second derivative is negative, then the first derivative is decreasing, and so the temperature of the coffee would be changing at a decreasing rate. So let's just use our graphing calculator to graph this function and see what its behavior is, positive or negative, on this interval from 12 to 20. All right, I've typed the second derivative into the graphing calculator, and here it is. We can see at a glance that the second derivative is certainly positive for t between 12 and 20. That's what the graph suggests, and looking at the function, that makes sense, because 0.2455 is positive, e to a power is always positive, 100 minus t is positive on this interval, and t squared is also positive. So yeah, second derivative is positive, so the first derivative is increasing. So since the second derivative is positive on the given interval, the temperature of the coffee is changing at an increasing rate. And that completes our solution to free response question 1 from the 2024 AP Calc AB exam. Now on to problem 2, which is unique to the BC exam. A particle moving along a curve in the xy plane has position x of t, y of t at time t seconds, where x of t and y of t are measured in centimeters. It is known that x prime of t is this and y prime of t is this. At time t equals 2 seconds, the particle is at the point 36. Part A says find the speed of the particle at time t equals 2 seconds and show the setup for your calculations. To find the speed of the particle, we're going to have to calculate the magnitude of the velocity vector. The velocity vector is just made up of x prime and y prime, as its x and y components, so to speak. And then we just have to square those, add them together, and take a square root. That's the magnitude, which is the speed. So here for part A, we are looking for the speed of the particle at time t equals 2, and we know that this is the magnitude of the velocity at time t equals 2. The magnitude of the velocity is going to be the square root of x prime of 2 squared plus y prime of 2 squared. And let's consult the graphing calculator for this. I'll just do the inside of the square root first, and then we'll take the square root of the result. X prime of 2, that's pretty easy to evaluate. That would be 8 times 2, which is 16, minus 4. So that's 12. But then we have to square it, which is 144. So x prime of 2 squared is 144, and then we will have to add y prime of 2 squared. So we'll plug that in. Y prime of 2 is going to be negative 2 plus the square root, we're looking here, the square root of 2 to the power of 1.2 plus 20. And this whole thing needs to be squared because that's y prime of 2. So the inside of this square root is about 151.409. Then we'll just go ahead and take the square root of that to get the speed. So that's 12.305. And the units we know are centimeters per second. So 12.305 centimeters per second. All right, on to part B. Find the total distance traveled by the particle over the time interval from 0 to 2, and show the setup for your calculations. To find the total distance traveled, we don't want to integrate velocity because that would give us displacement. Instead, we want to integrate the speed. So for part B, we will be integrating over that relevant interval from 0 to 2. And what we're integrating is the speed. If we accumulate the speed at all the moments during this interval, we will get the total distance traveled. So we're integrating the square root of x prime of t squared plus y prime of t squared. And we will use our calculator for this. So on the calculator, I'll press the math button and then go to option 9 for the integration function. And then very carefully, I will type this whole thing in. All right, I've typed the integral into the calculator. We're using x in the calculator rather than t because that's more convenient. And we get 15.902. And again, this is in centimeters. So the answer is 15.902 centimeters. That is the distance traveled by the particle from 0 to 2. Now on to part C. Find the y-coordinate of the position of the particle at the time t equals 0, and show the setup for your calculation. So for part C, we know the position of the particle at time t equals 2. We know that it's at the point 36. So we'll start there with that position at t equals 2, and then we'll use an integral of the velocity in order to get our way back to t equals 0. And remember, this question is about the y-coordinate. So we're going to start with the known y-coordinate, which was y of 2. At t equals 2, we know the position. And then we will accumulate with an integral of the velocity from 2 backwards to 0. And what we're integrating is y prime of t, because we're only interested in the y-coordinate of the particle's position. So adding up all the rates of change of the y position will just get us back to t equals 0 when we add that to y of 2. Y of 2, of course, we know is 6. That was given to us. So this will be 6 plus this integral, and we can consult the calculator for that. Plugging this integral into the calculator, we get negative 7.174. So 6 plus negative 7.174. And 6 plus negative 7.174 is negative 1.174. So that's the approximate y-coordinate of the particle at time t equals 0. Finally, part D. For t between 2 and 8, the particle remains in the first quadrant. Find all times t in the interval from 2 to 8 when the particle is moving toward the x-axis, and give a reason for your answer. If the particle is in the first quadrant, then for it to be moving towards the x-axis, its change in y-coordinate must be negative. It must be moving down to approach the x-axis. So we just have to figure out when y prime is negative, and we can do that easily with a graphing calculator. So here in the graphing calculator, I've plugged in y prime. Let's go ahead and take a look at the graph. Have to zoom out to get a good view of it. And there it is. So we're looking between 2 and 8. That's the relevant interval for this part of the question. When is y prime negative? Well, it is positive at the beginning, but then it passes 0 at x equals 5.222. Or, for our purposes, that independent variable really is t. So at time t equals 5.222, that's when it starts to become negative, and we can see that it remains negative certainly past the endpoint of the interval at t equals 8. Thus, the interval of all times when the particle's moving toward the x-axis, between 2 and 8, is here, starting at 5.222, because that's when the derivative of y switches from positive to negative, and then all the way up through 8, it's negative that entire time. And since the rate of change in the y position is negative, the particle is moving downwards and hence approaching the x-axis. So since the particle's in the first quadrant, it's moving toward the x-axis when y prime's negative, which we saw from the graphing calculator was on that interval. And that completes our solution to free response question 2 from the 2024 AP Calc BC exam. Let me know in the comments if you have any questions, and be sure to check out my Calculus 1 course and Calculus 1 exercises playlists in the description for more. If you're looking for a bit more practice, check out my 10 hours of AP Calc AB BC FRQs video, linked in the description as well. Thanks for watching. Now on to the no calculator section, beginning with question 3. The depth of seawater at a location can be modeled by the function h that satisfies the differential equation given here, where h of t is measured in feet and t is measured in hours after noon, so noon is at t equals 0. It is known that h of 0 equals 4. Part A says a portion of the slope field for the differential equation is provided. Sketch the solution curve y equals h of t through the point 0, 4, which is that initial condition that was given to us. So down here on the slope field, we will plot the point at 0, 4, or actually, it's already plotted there for us, so that's great. Now we just have to sketch the solution curve passing through this point. So sketch a curve through the point that follows the directions as indicated by the slope field. Hence, the solution curve should look something like that. So that's the solution curve for part A. Moving on to part B. For t between 0 and 5, it can be shown that h of t is greater than 1. Find the value of t between 0 and 5, at which h has a critical point. Determine whether the critical point corresponds to a relative minimum, a relative maximum, or neither. And of course, we must justify our answer. So in looking for critical points, we consult the derivative, which is given to us, dh dt. First, is there anywhere that this derivative doesn't exist? The answer to that is no. Cosine is a nice continuous function on all real numbers, and we don't know anything about the function h, which is present in its own derivative. We don't know anything about the function h that would suggest it doesn't exist somewhere either. So the derivative exists everywhere for our purpose, so then we just have to ask where is it equal to 0? Those will be the critical points. When is this expression equal to 0? Well, h minus 1 is certainly never equal to 0 because it was given to us that h is greater than 1, at least on the relevant interval, which is between 0 and 5. H of t is greater than 1. So h minus 1 cannot be 0. Thus, the only way this derivative will be 0, and thus we get a critical point, is if cosine is 0. Cosine is 0 at pi over 2, and since the input is t over 2, this function will be 0 when t is equal to pi. That way, the input will be pi over 2. If you think back to the unit circle, that gets us up here, where the x-coordinate cosine is 0. So it's at t equals pi. There are, of course, infinitely many other values of t that would make this equal to 0, but that's the only one that's in the interval between 0 and 5. So there's our reasoning written out. The only critical point on the interval is at t equals pi. Now we have to determine if this critical point is the location of a max, a min, or neither. To do that, we'll use a quick sign chart. Here's the critical point at t equals pi. What's the sign of the derivative to the left of t equals pi? Well, think about the unit circle. If t is between 0 and pi, then the input, t over 2, is going to be at this part of the unit circle, in the first quadrant, where the x-coordinate is positive. Thus, the derivative, seen here, will be positive, because 1/2 is positive, h minus 1 is positive, and cosine, as we just said, is positive. That's when t is between 0 and pi. Once t passes pi, the input, t over 2, passes pi over 2. And so now we're over here, where x is negative. And so the sign of the derivative would be negative. Hence, the function switches from increasing to decreasing. So at t equals pi, we have a relative maximum. And there that reasoning is. There's a relative max at t equals pi because the derivative, dh dt, switches from positive to negative, we might say, at t equals pi. That completes part B, so let's go ahead and finish with part C. Use separation of variables to find y equals h of t, the particular solution to the differential equation that was given, with the initial condition h of 0 equals 4. So we'll take this differential equation, separate the t's and the h's, and then integrate, and then we can use the given initial condition to solve for the arbitrary constant and get our particular solution. Let's go ahead and multiply both sides by dt and divide both sides by h minus 1 in order to separate the variables. Then on the left side, we're going to have 1 over h minus 1 dh. And on the right side, we're going to have cosine of t over 2 dt. Now we can go ahead and integrate both sides. On the left, the integral of 1 over h minus 1 is just the natural log of the absolute value of h minus 1. And on the right, integrating cosine of t over 2 over 2, we're going to have sine of t over 2. If we took the derivative of this, the chain rule would give us that 1/2 that we have here. And then let's imagine that we gathered all the arbitrary constants on the right. So this is it. Now we can go ahead and use our initial condition to solve for c. That initial condition was that h of 0 is equal to 4. So plugging that information into this equation, we have the natural log of h is 4. So this is the natural log of 4 minus 1, or simply the natural log of 3. And this is equal to sine of t over 2, but we're plugging in t equals 0, so that's sine of 0 over 2, and sine of 0 over 2 is just 0. So we're really just left with the arbitrary constant c. And of course, the absolute value with the natural log, we don't need that because 3 is positive. So c is equal to the natural log of 3. So then back in this original equation where we had c, we can just go ahead and replace that c with the natural log of 3. Now we're trying to solve for h to find the particular solution. What is that function h satisfying this differential equation? So we're going to exponentiate the left and the right sides in order to get rid of that natural log. So on the left, we're going to have e to the natural log of h minus 1. And of course, the whole point is that the e and the natural log cancel out. So why don't we just go ahead and write the absolute value of h minus 1. And then on the right, we're going to have e to the power of everything that's on the right. So e to the sine of t over 2 plus the natural log of 3. But by our exponent rules, e to the sine of t over 2 plus the natural log of 3 is the same as e to the sine of t over 2 times e to the natural log of 3. But e to the natural log of 3, of course, is just 3 because e and ln cancel out. So this is just e to the sine of t over 2 times 3. So then, to get rid of the absolute value, we could say that h minus 1 equals plus or minus 3 times e to the sine of t over 2. So is it the positive solution or is it the negative solution? Plus or minus? Well, we know the initial condition gave us a positive value for h of 0 equals 4. So in fact, this must be the positive solution. It's not plus or minus, it's just plus for this particular solution. Finally, we can add a 1 to both sides to finish solving for h. So finally, we have h equals 3 times e to the sine of t over 2 and plus 1. And if we want to go ahead and emphasize that this is a function satisfying this differential equation, we can write h of t equals this. And that completes our solution to free response question 3 from the 2024 AP Calc AB BC exam. Moving on now to question 4. The graph of the differentiable function f shown for x between -6 and 7 has a horizontal tangent at x equals -2, which we can kind of see there, and is linear for x between 0 and 7. So that's over here. It looks linear, and in fact it is. Let R be the region in the second quadrant over here, bounded by the graph of f, the vertical line x equals -6, and the x and y axes. This region R has an area of 12. Part A says the function g is defined by g of x equals the integral from 0 to x f of t dt. Find the values of g of -6, g of 4, and g of 6. The first one, g of -6, is really easy. By definition of g, well, it's the area under the function f of t, which is graphed, from 0 to whatever the input is. So if the input is -6, well, g of -6 is just the area from 0 to -6, this area here. Now, we were told the area of that region is 12, but we do have to be careful because the function g is going to calculate this area backwards, going from 0 to -6. Hence, it will actually consider this area as -12. So g of -6 is -12. All right, next up is g of 4. To calculate g of 4, we just have to calculate the area under the curve from x equals 0 to x equals 4. That's just the area of this triangle. So g of 4 is going to be 1/2 multiplied by the base of the triangle multiplied by the height of the triangle. The base of the triangle is just 4, from 0 to 4. So we will put 4 there for the base. And the height, we can see, is just 2. So our height there is 2. 1/2 times 4 times 2 is equal to 4. Finally, for g of 6, we have to do the same thing, adding up area from 0 to 6. So that's going to be the area from 0 to 4, which we already calculated. It's just 4. And then we need to add this area from 4 to 6. And we can see that's going to be a negative area because the curve is now underneath the x-axis. But again, this is just a triangle. So again, we will use 1/2 base times height. And again, we're taking all the area from 0 to 6. We already did the area from 0 to 4, so now we're just going to add the area from 4 to 6. The base of this triangle is 2 from 4 to 6, and the height we see is -1, which is why the area will be negative. So this is going to be 4 plus base, 1/2 times the base of 2 times the height of -1. So this is 4 minus 1, which is 3. That is g of 6. On to part B. For the function g defined in part A, find all values of x in the interval from 0 to 6 at which the graph of g has a critical point. And we are asked to give a reason for our answer. To find critical points of g of x, we need to consider the derivative of g of x. We know that g of x will have a critical point where its derivative is 0 or where its derivative does not exist by definition of a critical point. But we also know from the fundamental theorem of calculus, since g is the integral of f of t from t equals 0 to t equals x, the derivative of g just cancels out that integration. And so g prime of x is actually just f of x. and f of x exists on this entire interval from 0 to 6. I mean, we're looking at its graph. It certainly exists. So there's not going to be anywhere on the interval from 0 to 6 where g prime does not exist. Hence, the only places we have to look for critical points are where f of x is equal to 0. And from the graph, again focusing on the interval from 0 to 6, we see that f is equal to 0 at x equals 4. So that is our one critical point. That's the only critical point, and so that completes our solution to part B. Let's finish with C. The function h is defined by h of x equals the integral of f prime of t dt from negative 6 to x. Find the values of h of 6, h prime of 6, and h double prime of 6, and show the work that leads to our answers. So I'll jot down part C up here, beginning with the calculation of h of 6. H is an integral of f prime from negative 6 to x. So if x, the input, is 6, by the fundamental theorem of calculus, we can evaluate this integral as f of 6, so that's the antiderivative of the integrand, evaluated at this input, f of 6 minus f of the lower bound, negative 6, right? This is how we evaluate definite integrals. We take the antiderivative of the integrand and then evaluate it at the upper bound and the lower bound and subtract them. We can find these values from the graph. F of 6 is given as negative 1, and f of negative 6 we see is 0.5. So this is going to be negative 1 minus 0.5, and so the answer is negative 1.5. Now, what about h prime of 6? Well, the derivative just undoes the integral, so h prime of 6 is actually just going to be f prime of 6. H prime of 6 equals f prime of 6, and f prime of 6 is the slope of the line tangent to f at x equals 6. So let's look at the graph of f, and at x equals 6, we are over here. We know that this is linear, and so the derivative is just going to be the slope of this line. We can see 2 points here that allow us to quickly calculate the slope. The line goes over 2 and down 1. So that's a slope of negative 1/2. Hence, h prime of 6, which is f prime of 6, is negative 1/2. Finally, h double prime of 6, that's the rate of change of the rate of change of f, the rate of change of the derivative of f, at x equals 6. And if we look at f at x equals 6, well, we know that f is a line over here. Hence, it has a constant rate of change, and so its second derivative, the rate of change of its rate of change, must be 0. The derivative is not changing at all at x equals 6. It's a line with a slope of negative 1/2. And that completes our solution to free response question 4 from the 2024 AP Calc AB BC exam. Now on to problem 5, which is exclusive to the BC exam. The function f is twice differentiable for all x with f of 0 equal to 0. Values of f prime, the derivative of f, are given in the table for selected values of x, which we see here. Part A says for x at least 0, the function h is defined by h of x equals this integral here. Find the value of h prime of pi and show the work that leads to your answer. When we take the derivative of h to find h prime, by the fundamental theorem of calculus, this integral is going to go away, and we'll just be left with the integrand, and we'll have to plug in pi. And we can use the table to evaluate that. So here for part A, h prime of pi, that's just going to be the integrand in the definition of h, so the square root of 1 plus f prime of pi, we're plugging in t equals pi, squared. And what is this? Well, f prime of pi, we see from the table, is 6. So this is the square root of 1 plus 6 squared. So the square root of 1 plus 36, or the square root of 37. Now, part B. What information does the integral from 0 to pi of the square root of 1 plus f prime of x squared provide about the graph of f? You're supposed to recognize this as the arc length formula. Integrating the square root of 1 plus the derivative of a function squared gives us the length of the function, the arc length, from the lower bound of integration to the upper bound. So this is the length of the curve of f from 0 to pi. And there that is written out. The length of the curve f from 0 to pi, that's what that is. It's arc length. On to part C. Use Euler's method, starting at x equals 0, with two steps of equal size to approximate f of 2 pi, and show the computations that lead to your answer. Since we're using two steps of equal size, we will of course start at x equals 0, and then we'll jump forward pi, and then we'll jump forward another pi to get an approximation of f of 2 pi. So for Euler's method, we start by going from 0 to pi. We know from the problem that f of 0 is 0. And then we can approximate f of pi using the derivative of f at x equals 0. So let's write this out. What is f of pi? Well, it's going to be approximately f of 0 plus the rate of change, or the derivative, at 0, multiplied by the change in x when we go from 0 to pi. That change in x, of course, is just pi. The idea, of course, is that the derivative at x equals 0 tells us how much y should increase if we increase x. So this equals f of 0 we know is 0, and then f prime of 0 we know is 5 from the table. And then, of course, this is getting multiplied by pi. So if we increase x by pi, starting at x equals 0, the derivative tells us that y should increase by approximately 5 times that increase in x, so 5 pi. So our approximation for f of pi is just 0 plus 5 pi, which is 5 pi. And now we can do this process again to take another step forward and get an approximation of f of 2 pi. F of 2 pi is about f of pi plus the derivative of f at pi multiplied by the change in x. If we're going from pi to 2 pi, the change in x is just 2 pi minus pi, which of course is pi. So let's start to plug in some of this information. F of pi, we know from the first step, is about 5 pi. So this is about 5 pi. And then f prime of pi, we know from the table, is 6. So this is going to be plus 6 multiplied by 2 pi minus pi, which is pi. So f of 2 pi is about 5 pi plus 6 pi, which is 11 pi. Again, the idea is that the derivative at a point tells us roughly how much y should increase based on a small increase in x starting at that point. So we take that increase in x and multiply it by the derivative. That tells us how much we have to add to the starting position. And we repeat this as much as we want to get the approximation at the desired point. All right, on to part D. Find the integral of t plus 5 times cosine of t over 4 and show the work that leads to our answer. Here we have an algebraic function, t plus 5, times a transcendental function, cosine of t over 4, and that means it's a prime candidate for integration by parts. We'll let u equal t plus 5, so when we take the derivative and get du, we'll get a nice simple function. And we will let dv equal cosine of t over 4. We can integrate that and be no worse off. So for part D, this is our integral. Again, we're going to let u be t plus 5. That way, du is just dt. Very straightforward. And then dv is forced to be cosine of t over 4 dt. Then we can integrate this to get that v is equal to 4 multiplied by sine of t over 4. Now, we should just check real quick. When we use integration by parts, we have to integrate v du. Is that something we can integrate based on our choices here? Well, v is 4 sine of t over 4, du is dt, so yes, we could definitely integrate v du. This will be very easy. So applying the integration by parts formula, this will be uv, so t plus 5 multiplied by v, which is 4 sine of t over 4, uv minus the integral of v du minus the integral of v du. So finishing up this evaluation, I'll go ahead and put the 4 first, just because I think that looks better. So 4 times t plus 5 multiplied by sine of t over 4. Then we just have to integrate 4 sine of t over 4, and that's going to be 16 multiplied by negative cosine of t over 4. You can check if we took the derivative of this, it would work out. We would have negative sine of t over 4, because there's a negative in front, and the derivative of cosine gives us a negative sine. So we would get positive sine of t over 4 because of the two negatives. We'd also get 1 over 4 from the chain rule getting multiplied by 16, and 16 times 1/4 gives us that factor of 4 that we want, and so this is correct. Just throw on an arbitrary constant. We might as well also let these two negatives cancel out, so this will just be plus, and now it's a little bit nicer. And that is our final answer for part D. And that completes our solution to free response question 5 from the 2024 AP Calc BC exam. And finally, problem 6. The Maclaurin series for a function f is given by this expression, and converges to f of x for all x in the interval of convergence. It can be shown that the Maclaurin series for f has a radius of convergence of 6. Part A says determine whether the Maclaurin series for f converges or diverges at x equals 6, and give a reason for our answer. So we know that the radius of convergence is 6, and of course the series is centered at 0 since it's a Maclaurin series, but that doesn't tell us if it converges or not at the endpoints. So at x equals 6, for example, we would have to plug that in and see, does it converge or not? Well, let's plug it in and investigate. Here is the Maclaurin series with x replaced with 6. So we've plugged in x equals 6, and then we can simplify. 6 to the n and 6 to the n will cancel out, and we just have n plus 1 over n squared. This is a great candidate for the comparison test, because n plus 1 in the numerator, well, that might as well just be n, and the denominator's n squared, so factors of n would cancel out, and we'd have 1 over n. So it seems like we should try comparing this to the harmonic series. Of course, the harmonic series diverges, so we could only use the comparison test to actually get a conclusion if the terms of this series are bigger than the terms of the harmonic series, and in fact they are, because certainly n over n squared is equal to 1 over n. Hence, if we add 1 to the numerator on the left, we make it bigger than 1 over n. And this thing on the left is the terms of our series. So yeah, the terms of this series are bigger than the terms of the harmonic series, and so this series must diverge also. So the Maclaurin series for f diverges at x equals 6 by the comparison test. The harmonic series diverges, and this series consists of terms that are greater than the harmonic series terms. And of course, both the harmonic series and this series consist of positive terms, so we can use the comparison test. All right, on to part B. It can be shown that f of negative 3 equals this, which equals this, and that the first 3 terms of this series sum to this number. We are asked to show that the error in this approximation, the third partial sum, is less than 1 over 50. So that's the error of the approximation. F of negative 3 is the true value of the function, and minus s3 is subtracting that partial sum. And so the magnitude of this difference is the difference between the partial sum and the true value of f of negative 3. We're trying to show that error is less than 1 over 50. Note also, to get from here to here, you just do a little negative 3 divided by 6, and so you get that negative 1/2 with the common exponent of n. But it was nice of them to do that for us. So for this problem, since it's concerning the error in a partial sum of what you should notice is an alternating series, because we have a negative to the power of n, to put a bound on the error, we'll use the alternating series estimation theorem. The alternating series estimation theorem gives us a very simple bound for the error of a partial sum. F of negative 3, which was given to us as this, is certainly an alternating series, and its terms decrease in absolute value. If we ignore this negative, the terms of the series look like this, and these decrease in absolute value and converge to 0 as n approaches infinity. That's pretty clear because the degree of the denominator, 2, is greater than the degree of the numerator. Not to mention the denominator has this 2 to the n term. So certainly these terms will decrease to 0. So we can apply the alternating series estimation theorem, which tells us the error of a partial sum, say the nth partial sum, is at most the magnitude of the n plus 1th term of the series. The error is at most the magnitude of the first excluded term. And that looks like this. So this error, which we are trying to put a bound on by the alternating series estimation theorem, must be less than the magnitude of the first excluded term. This is the third partial sum, so the first excluded term is the fourth term, A4. And we can find A4 by plugging n equals 4 into the general term of the series. That would give us 4 plus 1 over 4 squared, so 5 over 16, and negative 1 over 2 to the power of 4. But since we have the absolute value bars, the negative goes away, so it's just 1 over 2 to the power of 4. This is equal to 5 divided by 2 to the 4 times 16. 2 to the 4 is 16, and 16 times 16 gives us that denominator of 256. And 5 times 50 is 250, which is less than 256. So 5 is not even a 50th of 256. So this fraction, 5 over 256, is indeed less than 1/50th, which is exactly what we set out to prove, that this error is less than 1 over 50. And so that completes part B. Moving on then to part C. Find the general term of the Maclaurin series for f prime, the derivative of f. Find the radius of convergence of the Maclaurin series for f prime as well. All right, so here's our Maclaurin series. Should be very simple to take the derivative. There's only one variable there. It's just x to the n, and so we'll take the derivative just using the power rule. So taking the derivative of this general term, the exponent of n drops down as a factor, and then we just reduce the power of x by 1, x to the n minus 1. And so we get here, and then n over n squared, we can cancel out a factor of n, and so it looks like this. That is the general term of f prime. So the derivative of f is equal to this series, at least on the interval of convergence. We were asked also to identify the radius of convergence for this series that we found by taking the derivative. You're expected to know that differentiation term by term does not change the radius of convergence of a series. Neither does integrating term by term. So since we were given originally that the radius of convergence is 6, we see that there, radius of convergence of 6. So when we differentiate term by term to get this series, that radius of convergence does not change. It is still 6. It's certainly intended that you would just know the radius of convergence does not change. That's why they gave us that piece of information. But you could use the ratio test if you weren't sure, and you would arrive at this solution, that x has to be between negative 6 and 6, so the radius of convergence, again, is 6. All right, on to the final part, part D. Let g of x equal this series. Use the ratio test to determine the radius of convergence of the Maclaurin series for G. So if you're a little rusty on the ratio test, you can look at this example that I just wrote out for part C. We're going to use the ratio test now for part D and this new function g of x. So here's the series for g of x. When does it converge? Well, the ratio test tells us we can look at the limit as n goes to infinity of the absolute value of an plus 1 in the numerator and an in the denominator. So in the numerator of this ugly expression, we see a general term of the series, but with n plus 1 plugged in for n. So instead of n plus 1 here, we plugged n plus 1 in for n, and so we actually have n plus 2. And instead of x to the 2n, we have x to the 2n plus 2, because the 2 distributes through the n plus 1. We then have n plus 1 squared, and of course 3 to the n plus 1. And then just a general term of the series, an, in the denominator. So this is the limit of the magnitude of the ratio of consecutive terms of the series. And the ratio test tells us that this series will converge when this magnitude has a limit that's less than 1. In this first step, we just rewrite the fractions and simplify a little bit. Of course, dividing by this fraction is the same as multiplying by its reciprocal. So you see the n squared pops all the way up to the numerator. As for the 3n, that also goes to the numerator, but then it cancels out with the 3 to the n plus 1 in the denominator, leaving a single factor of 3 in the denominator. N plus 1 squared is still in the denominator, and this n plus 1 is also still in the denominator. In the numerator, of course, we still have that n plus 2, and the x to the 2n plus 2 mostly cancels out with x to the 2n. It just leaves behind 2 factors of x, so x squared. And this simplifies nicely because in the numerator, we have n cubed plus some stuff if we were to distribute here. And in the denominator, we also have n cubed plus some other stuff if we were to distribute everything. So the n terms will completely cancel out. They have the same degree, 3 on the top and bottom. That just leaves us with the limit as n goes to infinity of the absolute value of x squared over 3. And there's no n here, so the limit as n goes to infinity of this is just this. And then to find the radius of convergence, we just ask when this is less than 1. Well, if this is less than 1, multiplying across by 3, we get that the magnitude of x squared is less than 3. Now, if the magnitude of x squared is less than 3, x must be between negative root 3 and positive root 3. And so the radius of convergence is root 3. We haven't investigated what happens at the endpoints. The ratio test doesn't tell us about that, but that's also not important for the question. The radius of convergence is root 3. And that completes our solutions to the free response section of the 2024 AP Calc BC exam. Let me know in the comments if you have any questions, and be sure to check out my Calculus 1 course and Calculus 1 exercises playlists in the description for more. And if you want some more practice, check out my 10 hours of AP Calc AB BC FRQs video in the description as well. Thanks for watching.
I'm the mathematical menace, the machinations of mankind. 2 calculators at the same time, hand signs and abacus, finger count and calculus. I'm a V to the T, my parameter the rapidest. Happens like this, my lecture's the most prominent, dominant. Call me to Morgan, I get the compliments. The union in together like any time that we intersect, cause my opponents know they need